Welcome to the first in a series of videos on logarithms. Logarithms are really useful in science and technology, but people find them quite intimidating. What I want to do in this series of videos is take you not on the direct route using algebra, but take you on a more scenic route, taking a lot more steps, showing you a lot more things on the way, and eventually leading you to the manipulation of logarithms. There'll be plenty of points when you're thinking, I don't understand what the point of this is, but bear with me and all of it will eventually fall into place. The first place we need to start is a long way away from the abstract concept of logarithms. We need to start off with a very simple practical problem. In the days before calculators, how do you easily write out repeated multiplication? It seems like an odd question to ask, but banking has been around for a long time, and if you want to work out an interest rate on a loan, then you might have to work out, let's say 1%, and you'd have to work out 1.01 for, say, the first month of interest, and multiply that by 1.01 for the second month of interest, and so on for 12 months, 24 months, 36 months. And you're writing out the same thing again and again and again and again and again, and it's incredibly time consuming and very hard work. During the 1400s and 1500s, there were various notations invented to show repeated multiplication. The one that we have inherited today is commonly known as exponential notation, and it works like this. If I have 2 times 2 times 2 times 2, I abbreviate that by writing out the number here we're going to call the number base, and up here I write down how many times I've multiplied this number together, which in this case is 4 times. And I would describe that as 2 to the power of 4, or 2 to the 4th. We'll take another example. Let's try 3 times 3 times 3 times 3 times 3. The number base in this case is 3, and I have multiplied that by itself 1, 2, 3, 4, 5 times. So I write that out as 3 to the power of 5. At this point I'm also going to introduce an extra piece of notation, or more accurately an abbreviation. It gets quite tedious writing out an X symbol every time I want to write out a multiplication, and also it's a bit confusing sometimes as to whether an X means an unknown or an X means a multiplication symbol, or perhaps it's the other way around. So where it's obvious, what I'll be doing is writing out 3 dot 3 dot 3 dot 3 dot 3, and the dot here will indicate a multiplication symbol, so that will still be 3 to the power of 5. I won't be writing out things like 5 dot 5 to indicate a multiplication, because that can be understood as 5.5, whereas 5 dot 5 dot 5 is unambiguous. That means 5 times 5 times 5. Another abbreviation I'm going to be using an awful lot will be to describe a number to the power of 2 as being squared, and a number to the power of 3 as being cubed. The reason being, if I have, for example, 2 squared, I can understand that as being quite simply a square, and the area, the length of this side is 2, the length of this side is 2, and I have 1, 2, 3, 4 bits, which is correct. 2 times 2 is 4, and if I square it, I have 4 pieces. And the same applies if I have 2 cubed. I would have 2 to the power of 3, or 2 cubed, and that would give me a cube. And you can see that the first layer at the front here has got 1, 2, 3, 4 bits. Obviously the layer behind it has got another 4 bits, so I'd have 8 bits, and 2 times 2 times 2 does indeed equal 8. So I'll be randomly swapping between 2 squared, 2 to the power of 2, 2 to the second power, 2 cubed, 2 to the third. It all means the same thing. But back to our notation. What we want to do is understand how this new notation works, what its properties are, what happens when we start doing calculations with it. So let's try some nice simple calculations. We'll try 3 squared times 3 cubed. And we can write that out in full as being 3 times 3 multiplied by 3 times 3 times 3. The answer is very easy to work out. It's going to be 3 to the power of 1, 2, 3, 4, 5. If we try another example, let's try 7 to the power of 4 times 7 to the power of 5. That's going to give me 7 times 7 times 7 times 7 multiplied by 7 times 7 times 7 times 7 times 7. And that's obviously going to give me 7 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9. What I want you to notice with these two examples is that the exponent here is a 2, the exponent here is a 3, and the exponent in the answer is 2 plus 3, which is 5, which makes sense because I have 2 3's, and when I multiply I put on to the end of that the other 3 3's, so I'm going to get as many 3's in here as I started off at the beginning. The same is true here. I have 4 7's here, I have 5 7's here. My final answer has to contain 9 7's. So we can now write this out in a slightly quicker way. I can write out this problem here as the following: 7 to the power of 4 times 7 to the power of 5 equals 7 to the power of 4 plus 5, which gives me 7 to the power of 9. I can apply this to numbers that have got special symbols, the most famous of which is probably pi, which is a number a little bit bigger than 3, it's about 3.14, and I could write out pi to the power of 8 times pi to the power of 7 times pi to the power of 6, and that's going to give me pi to the power of 8 plus 7 plus 6, and that's going to give me pi to the power of 21. The only other thing to say at this point about multiplying powers together is that it only works if we use the same number base. If you notice, every single one of these uses the same number base. All 2's in this case, all 3's in this case, all 7's in this case, all pi's in this case. We can't write out, for example, 2 squared times 3 squared as a simple power of 2. We can't just add the powers together because the number bases are different. This is a question that we're going to tackle in a much later video, but at the moment we're only concentrating on multiplications where we've got the same number base. Of course, this leaves us with an obvious question. What do we do about division? We'll see in the next video.